Hello, good morning, and my name is Ram Sriram, and I am from the National Institute of Standards and Technology. Today, I will be talking about AI metrology, ensuring the reliability of artificial intelligence. So, the outline of the talk is as follows. First, I'll give you a brief description of the evolution of artificial intelligence. Then, I'll talk about what NIST is doing in AI in general. Then I'll talk about metrology for AI and AI for metrology. And finally, I will summarize it. In terms of AI, I'm giving a very simplistic view. Generally, AI, especially this is from my 1980s definition, is concerned with the development of computer programs that emulate the intelligence of humans. So that's kind of obvious. I mean, here we are talking about artificial intelligence. So we try to emulate the intelligence of human beings. So one perspective of this is you have the environment and you have information and all kinds of data coming out of this environment that using our perception, in perception in a sense like the senses, we have several sensing mechanisms like for example our eyes, ears, touch and so on. And the information comes through these sensing mechanisms into the intelligent agent, and this is called perception. So a particular intelligent agent, based on the knowledge it has and the information it is gathering from the external environment, will make some decisions. And those decisions um, could be some action items will come out of these decisions. And this could be either natural language processing, or if you're talking about robotics, the robot doing something. And then that goes back into the environment. Now, so that's one definition of particular intelligence. There are other definitions, but anyway, I'll stick to that for the time being. And actually, Howard Gardner wrote a famous book called The Frames of Mind, and he talks about multiple intelligences in that book. In terms of the evolution of AI, there can be several stages. The first one is the prehistoric age, where that can be divided into Paleolithic and in Neolithic. And in terms of the Paleolithic age, we have the Indian and the Greek philosophers who have contributed to a lot in the field of, well, a lot to essentially representation, knowledge representation, logic, and inference. The Indian philosophers did this depending on various dates, anywhere between 1000 to 2000 BC, whereas the Greek philosophers are starting with about Aristotle in around 300 to 400 BC. So both these people talk about, essentially the Indian philosophers talked about logic, several types of logic, and they also talked about the inference or anumana. And the Greek philosophers like Aristotle talked about syllogisms, which is also the Indian philosophers talked about. Then we have the Neolithic period of Hume, Russell, and Turing. I don't want to go into deeply into the philosophical aspects of it, but just to give you a flavor of what has been happening over the years. So we saw the beginning of the AI, where the term AI was coined in 1956 at the Dartmouth Conference. So first you have the early years and rise of knowledge systems like in 1957 to 1980, GPS, General, Hearsay, Maxima, Mycin, Shidlu, Shaky, and other contributions were made during this period. But the real first wave or the first revolution started in 1980s, early 1980s, and that's when I got into AI. And Feigenbaum wrote this book, I believe it was the rise of AI or something like that. And so at that time, people thought, the AI revolution will transform the way that we're going to do things. Then, for some reason, this kind of fizzled out because then the idea there was knowledge is power, and there was some initial work done at early neural networks, including Jeff Hinton at CMU. This was some preliminary work that was done in neural networks. Then we have the silent period, which is 1990s to 2000, where lots of things were happening in AI, but there was not as much talk about it as today. Deep Blue, rise of the robots, commercialization of AI technologies, like in particular the speech recognition technology, For example, naturally speaking, Dragon, which came out of CMU, was one of the pioneering contributions for speech recognition. But this was kind of commercialized, and it went to several phases in terms of several companies were handling this. And right now, I think it's a Nuance, which probably is bought over by Microsoft. So then we have the second revolution, which started about 2000 and kind of went around. I gave about 2 decades of these things because there was a lot of activity which went into this period, and one of the things that happened is that the chips by NVIDIA and others which were being developed for video games processing, it was found out that this could effectively be used for doing computations in neural networks because a lot of metrics computations going on in neural networks. And then you also had a paper in 2017 to 18 timeframe about the transformer architecture, which led eventually to ChatGPT and the other other LLMs, large language models. So that is what I call as the second wave or the second revolution. And the third revolution, which we are kind of witnessing right now, is the symbiosis of neural and knowledge networks, and this is also called neurosymbolic reasoning. So the pure neural networks per se could be viewed as what is known as the System 1 reasoning by Daniel Kahneman, and the knowledge-based kind of reasoning or the knowledge network reasoning is System 2 reasoning. So we do need a combination of these two types of reasoning. And finally, we have what is known as the conscious machine, which I think may happen sometime in the near future. And it could be the fourth wave of the tsunami, where people are claiming these machines can become sentient, but I'm not sure how we are going to go there because there's a lot of stuff about the human brain we do not still understand. There was also a nice talk by Henry Quartz. Henry Quartz's talk is available at the website given there, and he kind of goes through the evolution of the AI. And now I'll briefly talk about what NIST is doing. As I said, I work in the National Institute of Standards and Technology, and the idea for us is to promote US innovation and industrial competitiveness by advancing measurement science, standards, and technology in ways that enhance economic security and improve our quality of life. And also NIST is in written in our Constitution, Article 1, Section 8, where it talks about weights and measures. So NIST is essentially a measurement lab in one sense and a standards lab in another sense, in addition to developing some technologies. So in terms of the AI program, this kind of has been happening in the last decade or so, and we have several goals. One is to conduct fundamental research to advance trustworthy AI technologies, and we want to advance AI research and innovation across all the NIST laboratory programs. We want to establish benchmarks, develop metrics to evaluate AI technologies, and that's one of the things I'm going to talk about in terms of AI metrology. The other part is to participate and lead in the development of standards to advanced AI innovation, contribute NIST technical expertise to discussions and development of policies, which we kind of put input to various other agencies also in this thing. Then we ensure that NIST has resources and expertise to carry out its AI programs. So there's certain things we have done over the last few years in terms of NIST AI risk management framework, which came out and is being modified. So some of these things have been done in the past, and they have been reconfigured into other task forces. We also do a lot of interagency coordination, at least used to do between OSTP and so on. Now, there are a number of things that have happened in the last few years. So for the latest updates, I would suggest going into https www.nist.gov/artificial intelligence, and that gives the latest update of what NIST is doing in AI. So here are some investments we made. One is the AI risk management framework. We'll come to that later on. And then we have also looked into AI evaluations, where we are looking at developing a set of standard benchmarks and data sets. Finally, we have AI standard development, where we are providing technical leadership to advance the development of standards for AI data performance evaluation, robustness, security, and privacy, and a host of things which I'll talk about later on. So again, there are a lot of recent updates under the White House winning the race. America's AI Action Plan that was released on July 23rd, 2025. NIST is named in a number of recommended policy actions. So you can see there's a URL for that website. And NIST recently launched its AI Standards Zero Drafts pilot project to accelerate AI innovation by developing AI standards more quickly while encouraging openness and collaboration. Again, there's a URL for that. And then NIST launches the Centers for AI in Manufacturing and Critical Infrastructure with MITRE Corporation, and there is another URL associated with that. So this is so far what I have done is given you a very brief overview of the evolution of AI. Then I talked about NIST and what NIST is kind of focused on in AI. Now I'll talk about the metrological aspects of AI. Now AI metrology is really the science of measurements. Metrology is measurement. So when we're talking about AI metrology, we are talking about science of measurements for AI. And there's a number of features in any science of measurements. One is the accuracy. So we need to develop a set of metrics along several dimensions. In terms of the accuracy dimension, there are several metrics, and these metrics generally depend on the particular domain and task involved, but may be further classified into robustness, which explores the resilience of the systems against perturbation and adversarial attacks, conciseness in text retrieval tasks especially, groundedness with respect to how well the system does on previously proven results. So this we have to look at things which have we have to have some examples and use cases where we have grounded results. Second dimension is performance, and here these metrics are essential in assessing the runtime performance of a particular system, and they can be further classified into memory efficiency, floating point operations, AI model parameters needed for doing this kind of performance. Then we have trustworthiness, and trustworthiness is extremely important for measuring AI, and this plays a very critical role in ensuring the reliability and understanding of the AI system. In general, there are four pillars of trust. One is communication. This involves making clear decision making and interpretability of results. Second is confidentiality, which involves privacy and security. The third one involves creating emotional response. Empathy is very important for AI, especially in areas such as medicine or healthcare. So whenever the AI system also should be empathetic to the patient's questions and the responses. And finally, your character, such as openness, which involves explainability, traceability, and reducing bias. So we have essentially four pillars of trustworthiness, and these four pillars are the four C's of trustworthiness. You can say four columns of trustworthiness, which involves four C's: communication, confidentiality, creating emotional response, and character. In addition to that, we also have things like uncertainty quantification, where this metric would be useful to evaluate the confidence level of an AI prediction. Because AI systems, let us say, are saying that, well, this person particularly has lung cancer, but then we need to have some confidence associated is how sure you are with that. And sometimes, when we'll come to that, some examples of what we are doing in this quantification. And finally, we have this risk, and there is a risk associated with any piece of software, whatever software you do. So it's very important to develop measures to evaluate the risk. And the risk, NIST has developed something called the AI risk management framework over the last 5 years or so, and that has been extended or modified in the last year. So you can again look at all these things in the website that I mentioned. In all these metrics, what is very important is developing standardized methods for evaluating each of these. So I belong to the software and systems division at NIST, and we have been focusing on a number of areas in terms of metrology for AI. On the traditional deep learning models, the generative AI systems, AI tooling, identifying metrics for large language models, acting as a neutral arbiter by conveyor, and supporting standards development. All these things are kind of are focused on the metrology for AI. So let's go and again here there are lots and lots of things that we are doing, and It's very hard for me to go into each one of these things, but I think you can look into the slide set that is provided. And I'm going to go through one example, which is characterizing uncertainty in AI-enabled medical devices. And this is the work by Peter Bacci and his colleagues in my division. So if you look at current image processing, or let's say the histopathological slice you take, and you input that into a neural network based systems. So when you do that, the system kind of learns some kind of a model in there. Okay, so once the system learns a model, then what happens is uh, you turn it with thousands and millions, whatever data that you have, and then you kind of give a new sample to the system. Now the sample goes into the trained AI model. Now one of the things is that you can have two things that can happen. One is that this system has already the system has already seen some kind of very similar things to the sample that you have shown, and so it's in distribution. There's a lot of confidence in your answer, and sometimes you are also out of distribution, and these out of distribution models are sometimes not flagged by the AI system. So here's an example where you have based on the pathologist's expertise, you have created a system. Now, what happened is that in a pathologist, when he looks at it, he or she can kind of tell you whether the person is a cancer or not, and so there's a reliability involved in there. However, for example, when you train a system, so the neural network has been trained with all the data, but it has seen an example which is not in the normal distribution, which it has not seen before, and it has not been trained on the thing. So what happens at this case is that you want to know what is the reliability of this prediction. So in other words, if you have high confidence in the prediction, where the system has actually seen some slides that it was trained before, it can directly go and take actions on that, and it can go to the oncologist, whatever the cancer prediction is. You can send a message to the oncologist saying that, yeah, indeed there is cancer. But however, if you have something which is not in the original training set, then you have to make a decision. And also there is some uncertainty that has to be quantified with that. And you need to find out this uncertainty, and then you may not want to send directly to the oncologist, but you may send it to a pathologist, and the pathologist will look at it and say whether it's reliable or not, and send it to the oncologist. So that is the kind of things that those are very important. How do you determine this uncertainty in this? So the way that one can do is the following. So what you do is that when you have, like for example, the grounded images. So you have a training data of input images on the side, and then this kind of goes through several levels of this deep learning neural network. As you can see in this particular slide, there are a number of stages it goes through, and at every stage what you do is that you have this probe, and then this probe kind of creates a signals like this. This particular one is a signal of this image, and this different images you can create different probes, which are using the probes, different signals have been created. So now if you give in a new image one, and you can again go and look at these probes, and these probes brings out signals which are very similar to the ones that has already been trained like this. And similarly, this one is very similar to this, and so on and so forth. So this, you say, it's very reliable. On the other hand, you give an image here where, for example, here this particular signal is okay, but the second signal that you have is not very aligned with this particular training data as such. Although it's kind of close to this, it's not really close as such. Especially you can see in this particular thing, in the fourth in this one, which is totally not anywhere close to these two things. So then you know that's kind of some unreliable prediction, and you can kind of give some quantification to that. Okay, so that's one of the examples that we have been working on. Like again, we're talking about the reliability of the systems. So you have trained with a particular training data set, and then you have some other image which is coming, which is not in the training data set. Now we want to know how good is your how reliable is your output, especially in fields like medicine. It could be pretty critical. So the second step, we're working on the Gen AI system, and I'm not going to talk too much about the metrology of the Gen AI system, but then go through the third part, which is the AI tooling. And again, we have a number of examples. One of the things that I'm going to talk about is the observatory, which is a platform for measuring and experimenting with LLMs with AI system focusing on agentic AI. So now, in the first one I talked about is mostly images, traditional neural networks, deep learning. So now we are coming into the era of large language models. So right now in the recent past, you have observed something called agentic AI. So a definition of this agentic AI refers to the autonomous AI systems that can independently plan, reason, and execute complex multi-step tasks to achieve goals with minimal human intervention, actively and acting proactively rather than just reactively. So these systems, these agent-based systems are active systems, okay, and they act in a very proactive manner. Now, in the 1980s, there was a lot of work which went on in the agent systems. Now, first one is the Blackboard framework, sorry, which Professor Raj Reddy at Carnegie Mellon and his colleagues have pioneered on. And here you have several agents which are called knowledge sources, which are acting to a blackboard, and there's an inference mechanism which controls when this particular knowledge source is fired or not, or when this particular agent is fired or not. And you can see this is a master agent. There are several other agents in there. And this particular architecture has been recorded in my book called Intelligent Systems for Engineering, where I have a chapter on Blackboard architectures. Then in Carnegie Mellon, you have another approach which was developed by Sarosh Talukdar and other people and his colleagues, where what happens is you have several types of agents like construction agents, improvement agents, evaluation agents, and destruction agents, which kind of go into a solution space. Now, each of the agent doesn't know anything about the other agent. They just create a solution, put it into the solution space. The other agent picks up and does some operation and so on. And eventually you get a solution. So this is a very powerful method, especially for optimization. And it has been shown and recorded in the book my book called Distributed and Integrated Collaborative Engineering Environment. It's a DICE project I developed at NIST. So now what we are seeing is the agentic AI with LLMs. That is, each of these agents are using large knowledge models. And what happens is that they are the clients, the LLMs, and using this model control protocol, they're communicating with other agents, with tools, with information and databases. So then what is needed, what we are working on this thing is this notion of having metrics put in between the LLMs are the clients and the tools and information base. What do I mean by that? Like, for example, the clients are asking questions to LLMs. A question could be, who are the ones who are going to be in the Super Bowl? Okay, so, but you want to know whether the question actually is asked in the right manner or not. And not only that, we need to develop some guardrails, because you don't want to ask questions which are prohibited. Okay, there are a lot of questions you might like. For example, one can ask a question to generate X, where X is inappropriate. So you want to stop it at the stage and say no, this is inappropriate. You cannot do that. Similarly, even in LLMs, we'll come to that again later on. There are certain metrics which should be developed for LLMs depending on the topic. So those are the metrics that we kind of study in. Similarly, the tools are returning answers. Then you want to know how do you measure the answers which you get back from the particular tool. Okay, so NIST has something called large language model zoo. We have a lot of LLMs in our laboratory. So in terms of so you perform you evaluate the LLM's performance, but I'm not going to go into too much details of that, except that so this particular framework is available. The other thing is identifying metrics for large knowledge models. So we wrote this paper several years ago on foundation metrics for evaluating effectiveness of healthcare conversations powered by generative AI. So the idea here is that, especially when you're talking about healthcare uh, chatbots, you have two types of metrics, the intrinsic metrics and the extrinsic metrics. Whereas the intrinsic evaluation metrics, they measure the proficiency of a language model in generating coherent and meaningful sentences, relying on language rules and patterns. And this is not really useful for healthcare chatbots. On the other hand, eccentric evaluation metrics present means of measuring the performance of language models by incorporating user perspectives and real-world contexts. So this again can be categorized in, as I mentioned before, accuracy, trustworthiness, empathy, and performance. And you have seen this example before. And again, under each one of them, you have some measures like robustness, conciseness. Similarly, under trustworthiness, I kind of talk about in the previous slide safety and security different separately. But anyway, in this paper that we wrote, we kind of have them as submetrics or metrics associated with trustworthiness. Similarly, metrics associated with empathy and performance. So then we developed some kind of an evaluation framework to evaluate these metrics. Okay, so the next thing I talked about is a neural arbitrator by conveyor. And what we also do is that we work with other agencies to help help in evaluating the projects. Like a typical example is this Trojan detection evaluation. And the idea is to find hidden behavior in AI models. And this was done by Walid and his group. And so this is part of a program which they had with IARPA. So the idea is the following. The idea, what are Trojans? See, what happens is that if you look at especially the large language models and deep neural networks, how they are trained. So these deep neural networks, for example, are deep learning systems. The way they work is that you have a training data, and then you have a learned model, and finally you have the output of this model. So what you can do is that you can insert Trojans at the input level, that is the data that you have, you can corrupt that data. At the model level, you can go in and change the weights of the neural networks, or at the output level. Like for example, if you have a car which learns how to recognize the stop sign, and you kind of put a post-it note on the stop sign, the system may think it's a speed limit sign. And these people have shown some examples in the literature on this thing. So what we have done is at NIST is to define and test metrics using data available from this particular Troj AI program. And then what we do is that the performers who are actually funded by the IARPA, they have developed a set of tools which can detect these Trojans. So we evaluate those tools based on the metrics that we have identified. So there's a lot of work we've done in this area. So the idea is that to help detect, to aid in the process of helping to detect Trojans, which can be either the input or the model or the output. Then standards are an important part in this whole metrology process, and they help in ensuring that you have robust AI systems. And one of the things that we are doing in this area is developing this system called Quirkus. And then what it does is it uses, it kind of extracts the concepts from standard documents. And not only that, it can look into the circularity of some concepts in the in these documents. Okay, so sometimes people kind of define term A in terms of term B, and again the B in terms of A, and that's what I mean by a circular argument. So for this, we have done several things. One is that we have actually I've been advancing a language, something called a category theory, which was made popular in maybe in the 1960s, and it's a very formal way of knowledge representation. And this particular representation scheme will do the following. Uh, like if you look at the ontology spectrum, there is a wide variety of representational schemes. For example, for things for taxonomies, you can use simple XML. On the other hand, if you want to do a little more reasoning, you might want to use first order logic or something like that. And also, there is a predicate calculus, and then you have the Newtonian mechanics. So, a lot of work in logic has been using predicate calculus, but then you also have Newtonian mechanics. How do you integrate these two things? And we believe there's something the category theory can do this, and we've been working on that. And using category theory and some linguistic concepts, we have developed this program called Quercus, where it will identify the implicit structure in language, and you can query this particular document for certain things, and the system will provide the appropriate answers. So essentially, this uses, as I said, category theory, and then you can represent the standard documents formally, formalization of standards documents. Like here is an example. Like there's something called the CDA clinical document architecture, and you can kind of ask it a query that, hey, can you tell me if this particular patient has this particular disease or something like that. So the system this particular document has got information to deal with some patient privacy. So the system kind of does several things, and it does both the knowledge retrieval and develop certain concepts and the relationship between concepts, and then it will identify inconsistencies in this thing. So anyway, again, it identifies errors, and it does the dependency management. Okay. So far I've talked about metrology for AI. So how do you measure AI? And the second thing that we're working on, AI for metrology, that is how do you use artificial intelligence for actually helping improve measurements. So for example, one example is the bioimaging analysis, where we have been using AI to help in a number of meteorological issues associated with several biological problems. And one of the things that I'm going to talk about is AI-based quality assurance of the retinal pigment epithelial cells. So the way that we do is the following. Now, on the left-hand side, you see the biological metrology, and then the right-hand side, you see the computational science. So the idea here is that we have the biologists and you have the computer scientists. So so what is happening in this case is that you have all these images from the microscopes which are coming, and we stitch these particular images, and then what we do is that we send it back to the biologists, who can look at it visually and define some biologically meaningful objects and features, and they'll send it back to us. And then what we do is that we do this through neural networks. We do feature extraction and visualization, and we develop a set of features and send it back to the biologist, and the biologist will check that to see whether they're right or wrong, and he'll kind of annotate the features and send it back to this, and the process kind of goes on. And the idea is to go through this iterative process, and at the end of the day, we have a system which we have a significant confidence in the workings of the system. And it is an example that we did using this system in the area of age-related macular degeneration. And it so happens that this cost is about $343 billion globally, and about 11 million people in the US have this problem. And when they have this, in fact, I have a gene mutation for that too. So when you get this kind of a thing, what happens is instead of having a 20/20 vision in the bottom, you'll see what you have in the top. So one way people are solving this problem is to take stem cells, the pluripotent stem cells, and grow them in petri dishes over 6 to 9 months, and then develop stem cell colonies. Now, not all stem cell colonies are good. Stem cell colonies are good, and take them and you implant them in the eye. So what happens in this case is that the stem cells that are growing in this petri dish, as I said, only some of them are good. So what we do is that we use the architecture that I show here. There's a lot of segmentation, tracking, and those kinds of things going on here. Is we kind of identify which is a good stem cell colony and which is not so good stem cell colony. So essentially, we identify stem cell colonies which can be implanted in the retina. And this particular thing was actually, we did the work with National Institutes of Health in their in one of the organizations and in one of the institutes, and it has been approved by the FDA and been used on a patient actually. So, and that's why I tell people I'm not really worried about this AMD, because I know using this particular technique, you can identify the right stem cell colony that can be implanted in your eye. There are a number of other examples in other image areas, and one of the areas is this concrete, like for example, in the nuclear power plants, they want to inspect them. So they take some particular cores and do some image processing on it and give it to a neural network kind of system, which will determine whether these things will fail in the future or not. Okay, so here are the number of examples which we are still working on that, and I'm not going to go into this deep detail, except that we have been working on the emotional recognition too. So the other major aspects of using AI for metrology is in the software world. Now, software bugs are costing the United States billions of dollars. Probably it's costing everyone billions of dollars. So now the existing technology like static analysis and so on is insufficient, is not sufficient. So to do that, we are developing a set of tools for finding bugs in code. So what happens? There's a lot of things that can happen in the software development. Nowadays, what people are doing is that they're using certain Copilot kind of things to generate code. So there are a number of AI systems out there which can help generate the code. Now, how do you know this particular code is trustworthy? So then you need to develop some grounded data, or at least examples, and you have to compare with these things. So here is one of the things that there's a lot of stuff we do in developing bugs framework. So we kind of map the code into these graphs, and we test this using neural networks. Okay, in terms of input, that particular graph is input into a neural network, and then we identify bad code and good code and those kinds of things based on the data sets we have. So that is AI and software engineering. So essentially, again, trying to keep this to about 30 minutes or so, we have metrology for AI and AI for metrology. So that means we do work on developing a set of metrics and measurements for AI, and also how do you use AI in the measurement worlds. Standards introduced at the right time will lead to innovation. Standards are extremely important. As an example, the musical notation, which was introduced around 12th century AD, has actually spawned enormous amount of innovation. So standards, when introduced, as I said properly, will lead to innovation, great strides in innovation. Now, we do develop a lot of testing algorithms, and we believe that increases the trust in AI. Bias-free AI systems are needed. We need a lot of public-private partnerships. So I've been involved in a couple of reports like US leadership in software engineering and AI engineering, which was a workshop which was held on June 20th to 21st of 2023. And this report is freely available on the web. And we focused on software engineering only and how AI can help in developing better software. We also, in about 2 years ago, there was a national AI research and development strategic plan, which is with the 2023 update, and I was one of the co-authors of that. We'll probably get an update. It was announced sometime next year, and of this particular of a strategic plan. Actually, maybe a new strategic plan, and I was also involved in that particular strategic plan. So anyway, this talk is based on the work by several people at NIST, and I provided the credit in appropriate slides, and this is a standard disclaimer here. Thank you very much, and I hope you all have a great workshop. This talk is dedicated to my mentors who passed away in last month, Professor D.V. Reddy and Professor Stephen J. Fenwiss. Again, thank you, and hope you have a great workshop.